Hello guys and welcome back to the Thermodynamics series. In today's video, we will take a look at heat capacity and how to use it when working with the first law of thermodynamics. Let's get started. Heat capacity is the amount of energy needed to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. Heat capacity is unique to each species. Let's take a look at two ways in which heat capacity can be useful. Heat capacity at constant volume. In a rigid container, when heat is applied, the molecules will move faster and faster. This will increase the internal energy. From this, we gain an extra formula. The formula always gives an answer in joule per mole, while CV is in joule per mole Kelvin. This can be applied to the first law since you can work out the internal energy. Thus, for our energy balance, change in internal energy equals Q, this formula can help us calculate the heat. We also get heat capacity at constant pressure. As heat is added, the system expands to keep pressure constant. The work and internal energy provided by the expansion is related to heat capacity at constant pressure. Work and internal energy grouped together is called enthalpy. In general, enthalpy accounts for both the internal energy and flow work for streams flowing into and out of open systems. Another use for enthalpy is to relate heat to thermodynamic properties in closed systems. In closed systems with constant pressure, enthalpy is equal to heat. Enthalpy is an intensive property and is also listed in the steam tables. This gives us an extra formula to relate the first law to heat capacity. This formula also gives an answer in joule per mole. Once again, heat capacity can help us with our first law energy balance. If we can calculate enthalpy, we can calculate heat at constant pressure. Heat capacity isn't always constant. It changes with temperature. So, if temperature changes, how can we calculate the heat capacity? Over time, people set up tables to help calculate the heat capacity as temperature changes. All you need is the tables and this formula. You find the elements you want on the table and plug the values into the equation to get that element's Cp value at a specific temperature. The A to E values are supplied within the table. But how are Cp and Cv related? How can I use the Cp value table to get Cv? Cp and Cv are related through the gas constant we all know, 8.314 joules per mole Kelvin. Cp is equal to Cv plus R. And it is easier for ideal gases, where Cp is approximately equal to Cv. Let's look at an example. In a piston cylinder assembly, 2 mole of methane gas expands isobarically, from 200 Kelvin to 500 Kelvin. Calculate the total heat transferred. Since pressure is constant, we know that the change in enthalpy is equal to the heat transferred, so we just use the enthalpy formula. We go to our heat capacity table and find the values from A to E for methane. We plug in our values and get a positive heat of 11,470 joules per mole. To get this in only joules, we just multiply with the amount of moles, which is 2, and thus we get a final heat of 22,940 joules. Also note that when I wrote the values from the tables, I used times 10 to the power -3 and -6 instead of +3 and +6. The last thing we are going to look at is how heat capacity is used for conduction. Let's talk about specific heat capacity. When an object is heated or cooled, the quantity of energy transferred depends on quantity of the material, in other words mass, magnitude of the temperature change, and the identity of the material. This is where specific heat capacity comes in. The specific heat capacity for each element or species is unique to that element or species. To calculate the energy transferred, we used this formula. Recall the example we did in the previous video about conduction, where a steel cup filled with hot tea is allowed to reach equilibrium through conduction. And that is heat capacity. I hope this video helped you understand how heat capacity can be applied to the first law of thermodynamics. In the next video, we will look at the application of the first law, simplify equations, and do examples with open and closed systems.